Okay, now let's talk about the resistance and Ohm's laws, right? Ohm's law states that the voltage across the element is equal to the current into the resistance of that element, which is the constant, right? I equal V is equal to I multiplied with R is constant of the element of that element. Okay, we call this law as Ohm laws, right? This is the voltage and current. Therefore, the voltage and current are in linear relation. What mean by linear relation between voltage and current? If we plot voltage and current, we have straight line, right? We call linear relation here. Or I to V. So R is the slope of this relation of this line, this straight line. Okay. And the resistance of the material is depend on its resistivity or rho here, the symbol rho. The inverse of resistivity we call conductivity here, symbol of sigma. And for cylindrical resistant element, the resistance is proportional to the range and the area, the cross-section area. So we can compute the resistivity as the L divided by sigma A, or is equal to rho L divided by A, right? This is, I think you can remember this equation, right? It's in physics classroom, I think. And if you plot VI curve, in this case, the slope is 1 by R. But if you plot I in x-axis and the voltage in y-axis, the slope would be R, right? Here. Because V is R into I. Here. This is the slope. And the intersection is 0, 0, right? And also we can define the conductance of the element. The conductance is the inverse of the resistance, right? The conductance is the inverse. Or G is 1 over R here. And the unit in Siemens or mole, right? R have the unit in ohm. And G you have the unit in mole, right? Or Siemens. Or S, we can use this symbol also. Or we can write out I equal to GV, right? Because I is equal to 1 by R into V. This is the example of resistance in practical life, right? For example, the ion, right, is a pure R. Right? Heater is will dissipate the power from your receptacle here, and then you dissipate into heat, right? P equal to V into I, and I is like I is V divided by R here, the current flow, and the voltage is from your home electricity supply, right? And mostly is dissipated into heat for the resistance, right? And the heater also. And here is also the lamp bulb also. To light and heat is transfer the power, which is V into I, is transferred into light and also heat, right? Mostly into heat. The light is maybe just maybe 20%, not more than 20%, and almost is 80%. This is the old model of lamp, right? We almost do not use this kind of lamp anymore, right? Because very, very low efficiency. You can see that this lamp is very low efficiency. Most of power is dissipated into heat. It's not to light. Okay. And also this table shows the resistivity of the common material in the room temperature. For example, the aluminum have very, very low resistivity, right? This is the conductor in this case. The copper also low resistivity is high conductivity. The low resistivity means it have a high conductivity. Okay, this is the resistance in electronic circuit, right? You will use this kind of element in your laboratory, and how to read the color band code to know that how much the resistance of this element. You will learn it in your laboratory section. Okay, I will skip this part here also. And the power dispatched into the resistance can be computed by V into I also. And V, you can substitute V by the voltage across the resistance here, for example. This is R, this is V, and this is I, right? And V is IR, or I is V by R, right? We can substitute V by I into R, so you get this I square R, right? I into I square R. Or you can substitute I by B divided by R, you get this value, right? So the power dispatched into the resistance can be computed by V squared divided by R when you apply the constant voltage to the resistance. Okay. Here, this example is to compute the resistor size or rating. Each resistor, for example, this type of element, it can it can use for maximum power, right? The P, with P equal to V into I. This is the rated power. It have the limited rated power. If you use it higher than its rated, it will heat and it will burn out the resistor here, right? So when you select the resistor, you need to know about how much the rated of that equipment to use. If you use it higher than its rated, the resistance will burn, right? The resistor will burn here. Okay, for example, if the resistor cannot be used for the power exceeding 1/4 watt or 0.25 watt. This is the rating of the resistance. So determine the minimum resistor size that can be connected to the given battery without exceeding the resistor power rating here. So in this case, the resistor power is 0.5 watt. Okay, not more than 0.5 watt. If you use it, if the power consumed by this resistor is higher than 0.5 watt, it will burn, right? And the battery voltage is 1.3 and 3 volt. This case and this case. Okay, the smallest size 1/4 watt resistor can be connected to each battery. So if we have the battery small size, we connect it to the battery. The voltage across the resistor is 1.5 volt. So the power dissipated by this resistor would be V square over R, right? V square over R. But V square over R must not greater than 0.25 watt, right? And V is 1.5 square divided by R must not greater than 0.25. So this resistor should be not lower than 9 ohm, right? We can compute here. So R must be greater or equal to V square divided by 1.5 square divided by 0.225 by R, right? So we can compute R. The resistance must not less than 9 ohm. In this case, it's equal to 9 ohm, right? And for the voltage with two battery is 3 voltage. The resistor must be not greater than 36 ohm. So in this case, if the resistor is 9 ohm, the power dissipated by this resistor will be 0.25 watt. And in this case, if the resistor is 36 ohm, the power dissipated is 0.25 watt also. Yeah. Right. Okay, are you follow? So in this case, if you select the resistance 9 ohm, the current will flow. I is V by R. So I is 1.5 divided by 9 here. But in this case, the current would be 3 divided by 36 here. Okay. In this case. Okay, I leave this slide for your self understanding checking. Okay, so you check your understanding with this slide, and then this is the answer after you try to follow this instruction. Okay. Okay, now let's talk about the series resistance, voltage divider, and parallel resistor and current divider. Okay. Okay, by definition, two or more circuit elements are said to be in series. It's connected in series like this. If the current from one element exclusively flow into the next element, all current flow from this element is flow to the next element. Okay, without any loss. Okay, from KCL is then follow that all series elements have the same current, right? All series elements have the same current. Okay, and by applying KVL, we can verify that the sum of the voltage across resistor equal to the voltage externally provided by the battery. Right? Let's see this figure. All the resistors are connected in series, right? In this case, the current flow from R1 and R2 and R3 are the same, right here. So by KVL, we found that 1.5 positive, right, equal to V1, V2, V3 sum together here. And then V1 is I into R1, right? V1 is I into R1, V2 is I R2, V3 is I R3. So in this case, 1.5 is equal to I R1, I R2, and I R3. We can take I over from the bracket. Then we can have I into the summation of R1, R2, and R3. So this is the can be used as the equivalent resistance of this circuit, right? It's similar to the 1.5 volt is connected to one single resistor with Req here, with Req. So this is the series resistor rule, right? So the equivalent series resistance can be computed by the summation of Rn, n equal to 1 to capital N, to total number of resistors. Okay. Yeah. So in this circuit, we can compute also I, right? So I is 1.5 divided by Req. This means that 1.5 volt divided by R1 plus R2 plus R3 here, right? But V1 is IR1, right? V1 is IR1. But what is I? I is this value, right? So we can substitute this value here into I, this value. Then we can get V1 is R1 divided by sum together for all R, for all resistor into the voltage across it. Similarly for V2, V3, and V3, right? For example, if we have this is V, we have R1 R2, R3 like this. We can compute, we can compute V1, V2, V3 by V1 equal to R1 divided by R1 plus R2 plus R3 into V like this, and V2 is equal to R2 divided by R1 plus R2 plus R3 into V also. V3 also R3 divided by total resistance into V here like this, and this relation called voltage divider. We can compute V1 directly when we know the voltage across all element, right? Because if we know V, the voltage of the battery, and if we know R1, we know R2, we know R3, we can compute V1 directly. We can compute V2 and we can compute V3 directly from voltage divider relation in this case. Okay. Okay, then the voltage across each resistor in series circuit divide in direct proportion of the individual series resistance. Okay, this is what I explained here, right? Okay, here this is the voltage divider rule in general form, right? For this series connection, right? The voltage across Rn, Vn, any n is equal to Rn into Vs if you connect Vs here, right? The voltage of Rn is Rn divided by the summation of all resistors into Vs. We call this relation as voltage divider method. Okay, now see some example about voltage divider. Okay, determine the voltage V3 in this circuit, V3 here. And what we know is we know the source voltage, the resistance value, and unknown voltage V3. Okay, in this case we know R1 is 10 ohm. This is 10 ohm. We know R2 is 6 ohm. R3 is 8 ohm. And then Vs is 3 volt. It's very easy to compute V3 in this case, because V3 will equal to V3 is equal to R3 over R1 plus R2 plus R3 into 3 volt, right? Vs, right? So here we know that we know all value in the right hand side, right? Is equal to 8 divided by 10 plus 6 plus 8 into 3 right here. Then we have 1 voltage for V3 equal to 1 volt, and this is the shortcut to compute V3, right? We can compute V3 in another way, right? We can just find out how much the current flow first, right? And we multiply the current with this resistance, right? Total current flow, and you multiply the current with the resistance, you will also get 1 volt, right? Also 1 volt, I think. So you can check this understanding, right, by compute with Ohm law. Okay, now let's come to the parallel resistor and current divider rule here. Okay. By definition, two or more circuit elements are said to be in parallel if the elements share the same terminal, right? It's connected to the same voltage, right? From KVL, it's followed that the element will have the same voltage, right? We have the same voltage if we connect the element in parallel. So you can apply the KCL rule in this case. The summation of all current of the node will be 0, right? Or in this case, IS equal to I1 plus I2 plus I3 here. Okay. So IS equal to I1 plus I2 plus IT. But I1, what is I1? I1 is will be the voltage here, right? The voltage between these two nodes. I1 is V divided by R1. I2 is also V divided by R2, and I3 is V divided by R3, right? So you can substitute I1, I2, I3 here. So I1 is V by R1, I2 and I3 is here. So IS is V. IS is therefore V over R1 plus V over R2 plus V over R3. So you can get IS is V into 1 by R1 plus 1 by R2 plus 1 by R3, right? Here this is a R total, right? 1 is 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 V into 1 by R equivalent here. So R equivalent can be computed by this formula, right? 1 by R eq is 1 over R1 plus 1 over R2 plus and so on here, right? And this is the equivalent resistance circuit, right? So we can also use one rule called the current divider rule for this circuit. This is current divider. In this case, we know that I1 is V over R1, I2 is V over R2, I3 V over R3, and V is Req divided by Is into Is, right? V is I source divided by R equivalent. Okay, here. So V, you substitute V with this value, right? With this value, we can get I1 is Is by Req divided by R1. Okay, here. Divided by R1. And then you can therefore I1 would be Req and 1 by R1 is 1 by R1. Here is 1 by Req, right? Req is 1 by 1 by R1 plus 1 by R2 plus together and 1 by R3 here, and Is. So you can compute the current I1 when you know R1, R2 and R3 and Is directly from this formula. We call this formula as current divider rule here, right? Similarly for I2 and I3, you can compute by this value here. If you have n number of resistance, you can use this formula here, right? But if you have two number of resistance, if you have only two element here, R1, R2, this is Is and this is I1, this is I2, right? The formula become, if you would like to compute I1 would be equal to 1 by R1 over 1 by R1 plus 1 by R2 into Is, and it is R2 divided by R1 plus R2 into Is. You can use this formula. You can compute I1 from this formula. Similarly, I2 can be computed by R1 divided by R1 plus R2 and Is. You can compute I2 by this formula. Okay, and this is the current divider rule or current division rule. Okay, and let's see an example on current divider. Here we have a current source here, and the current flow to I1, I2 and I3. We can compute I1, I2 and I3 directly if we know R1, R2, R3, and if we know Is also. And in this case we know Is of 4 ampere, right? R1 is 10, R2 is 2, R3 is 20, right? This circuit can be solved by, you can sum the, to get the total resistance, right? You can compute the equivalent resistance first, then you can get the voltage across its terminal, right? You can get V, and then you will get I of its element later. You can solve by this method also. But in this case, let's apply the current divider concept to this problem. Okay, to compute I1, you can use the current division. So I1 is equal to, right, 1 by R1 divided by 1 by R1 plus 1 by R2, 1 by R3 into Is, right? Because you already know R1 is 10. R1 is 10, R2 is 2, R3 is 20, and Is is 4, right? Just substitute the variable and you will get I1, and in this case I1 is 0.6154 amp here. So you can also compute I2, I3 in similar way, right, for this circuit here. So we call this method as current divider. So now we know about voltage divider and current divider. So instead of using Ohm laws, you can use the voltage divider or current divider rule or as well. Or if you cannot remember voltage divider and current divider, you can still use Ohm laws, right, to compute the current flow to each branch also, right? So any method you can use if the problem did not command you to do that, right? But if the creation define that you need to use voltage divider, then you need to use voltage divider, right? But if the problem just would like you to find out I1, you can use any method, right? So in fact we can find I1 with any method, right? You will get the same answer if you do it correctly, right? Okay, but in this case we forced to use current divider, so we need to use current divider. Okay, now let's see series and parallel circuit here. Just some further contents on this series and parallel. So in the circuit you may have both series and parallel circuit. Usually we are not going to get only all series circuit or all parallel circuit, right? So in our real life, maybe some series with parallel circuit mixed together in the circuit, right? So what we have to do is we need to find out the equivalent resistance, right? In this case, for example, we have R1 and R2, R3, series to R2, R3, which are in parallel circuit. So we have to compute the parallel element first. So this equivalent first, R2 parallel with R3. The value of R2 parallel with R3 first, and then plus with R1 here, right? So, and you can use any method to solve this circuit. And for the complex circuit, for more complex circuit, we will talk about nodal analysis and mesh analysis later on, right? Node and mesh analysis. Okay, this slide is for you to check your understanding again, right? Just try to follow the instruction and let's see that your answer is correct or not here. Okay, you have 3 slides for checking your understanding right now. Okay. Okay, now come to some example on the circuit for which is a well-known circuit in the industrial measurement circuit and it's or instrumentation circuit. This circuit usually connected to the sensor, which is the many sensor in the industrial is in the resistive type. We call resistive type. Sensor. It means that the resistance of the element is vary due to some parameter. For example, vary with temperature. Vary with temperature, we can use it to measure the temperature, right? But we need to connect the resistor with some circuit, right? Transform it into the voltage or current in order to be the representation of the temperature of this area, right? Or the pressure or the force or any parameter that or any variable you would like to measure or instrument. You can use the resistive type sensor here, but you need some circuit to handle the property of the sensor, right? So Wheatstone bridge is one of the circuit to do that. Wheatstone bridge is a resistive circuit that is frequently encountered in variety of the measurement circuit, right? In general form, the bridge circuit shown in this figure. Okay, this circuit called Wheatstone bridge, right? The impedance value is VA and VB. VA and VB. The voltage between VAB or VAB here, right? It can represent the circuit property in this case. So if we know R1, if we use the known value of R1 and R2 and R3, for example, Rx is the resistance of the sensor, right? Or it's variable, we unknown, right? Unknown. So we don't know how much the resistance. If we know this resistance, so we know that what is the temperature in degrees Celsius, or what is the pressure, or what is the force in kilogram, for example, here. So from this circuit, you can write this circuit as well. This is similar one. This is a similar circuit, right? Equivalent circuit here. V1 and V2 and Rx is unknown value, right? So find the value of VAB. VAB is VAD, right? VAD minus VBD here, right? So we can get VAB here. VABD and BD, right? This is same node, right? So VAB is VAD minus VBD here in terms of for resistance node, right? So if we use VD as reference, so VAB is VA minus VB. VA means VA compared to reference. VB in this case is VB compared to reference. VB, this is VA. So we use the reference concept, right? Reference concept. We just, or maybe we use this symbol as a ground also. Reference concept. All voltage in this circuit mean the voltage compared to VD. Or we can use VC. VC mean V of this node comparing to this node. Okay. After we define the D as the reference, right? Here, reference point D. So in this case, if R1 equal to R2 equal to R3 is 1K ohm, right? 1K ohm, 1K ohm and 1K ohm, and VAB is 12 millivolt. Find the value of Rx here. So if R1, R2, R3 is 1K, 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 or from this circuit is 1K, 1K ohm, or 1000 ohm on the other word. Vs is 12 volt. VAB is VAB here. VAB, if we measure VAB, here, is 12 millivolt. If VAB is millivolt, so if we can measure VAB of 12 millivolt, how much Rx? In this case, we can compute Rx. Okay, so we can compute Rx here. So how to compute Rx? From voltage divider, we know that VAD here, the voltage across R2, right? The voltage across R2 is Vs into R2 divided by R2 plus R1, right? From voltage divider, from this, from this knowledge, right? From this knowledge. Oh, sorry, no. From this voltage divider. Okay, from this knowledge, right? From this knowledge. Here. Okay, the voltage across the resistor is the voltage, the total voltage multiplied with the resistance of the voltage we are going to find out, and total resistance of overall circuit, right? Okay, sorry. Come back to this slide. Okay, here, and then VBD also. VBD is the voltage across Rx, right? Across Rx, it means that Vs into Rx divided by R3 and Rx, right? Here. Rx into R3 and Rx, right? So then we are going to find out VAB. We know VAB of 12 millivolt here. Of 12 millivolt here. So VAD and VBD minus together, right? VAB is VAD minus VBD, right? So it's equal to Vs, right? These two terms, the subtraction of these two terms, right? So we get Vs into R2 divided by R1 plus R2 minus Rx divided by R3 plus Rx. So we can substitute all known value, which VAB we know is as 12 millivolt, right? 12 millivolt, and Vs is 12 volt. R1 by R1 plus R2, Rx by R3 plus Rx. So we can solve for Rx, and in this case we solve for Rx as 996 ohm here. 996 ohm. Okay. Then what happens if VAB equal to 0? if VAB equal to 0, if VAB equal to 0, here you will get 0 equal to Vs, right, into R1 divided by R1 plus R2 minus Rx divided by R3 plus Rx, right? We can get this equation, and then this value is going to be 0, right? Vs divided by Vs from both sides, you will get R1 by R1 plus R2 equal to Rx divided by R3 plus Rx. So if we measure this voltage between A and B becomes 0, if it becomes 0, you get this relation, right? This relation is for VAB equal to 0, right? So what happened to this relation? We can get R1 R3 plus R1 Rx, right? We move this to multiply with this, and this multiply with equal to Rx R1 plus Rx R2. Rx R1 and Rx R1 can be cancelled to each other, and we get R1 R3 equal to R2 Rx, right here. This is the relation for obtain VAB equal to 0, right here. If VAB equal to 0, we get Rx from this equation. So in the measurement circuit, sometimes if we have this kind of circuit, right? For example, this is you don't need to check your understanding. I saw this. I saw it here, right? So when we have Rx, we have VAB. We measure the voltage together, and maybe we select one value of the resistance. For example, I use R3 as adjustable resistance here. So in this case, if we adjust, if this is unknown, right? Unknown. But I adjust one resistance until this voltage becomes 0 volt. It means that when this voltage is 0 volt, this relation is satisfied, right? It's R1 Rx equal to R2 R3, right? So in this case, R1 R2 R3 is known value, right? R1 R2 R3, we adjust R3 until we get the 0 voltage. So this equation is satisfied with this condition. Then we can compute Rx. We will know the value of the resistance, okay, of Rx. If we first we don't know Rx, but we take it into this circuit, so we can get Rx value from this circuit, or we call this is the balance Wheatstone bit. This is the balance Wheatstone bit here, or R1 by R1 by R1 by R2 equal to R3 by Rx, right? R1 by R2 equal to R3 by Rx here. Okay. For this service standard gate, I think we have no time to talk about the standard gate in this today. So I stop my record here first.